In this video, we'll be discussing Hess's law. Now, in order to understand how we use Hess's law, we have to understand that enthalpy is a state function. So when it comes to state functions, it doesn't matter what pathway you take, only where you begin and where you end. To demonstrate this, let's look at a generic reaction of going from reactant A to product C. Now, in any sort of chemical reaction, there is an enthalpy change involved. And as we know, the enthalpy of reaction is the enthalpy of the products minus the enthalpy of the reactants. But what if this reaction involved two steps? A goes to B, and then B goes to C. Well, in this example, every time we go up in enthalpy, it is an endothermic reaction, and every time we go down, it's an exothermic reaction. So notice the difference between A and C really hasn't changed. Even though we took a new pathway by way of some intermediate B, the net enthalpy change of this reaction is still the same. And if we want to measure the enthalpy of A to B and the enthalpy of B to C, and then add these two, then we get our original enthalpy of going from reactant A to product C. Now we also notice that if we take our original reactions, our steps 1 and 2, and we add them up, and then we cancel B, which shows up on both sides, we get our original overall reaction. Now this is an important concept, adding reactions. It's going to become important later on. Now you're probably thinking to yourself, well, how is this useful for a real reaction? Well, let's take the example of the combustion of methane. If we combust methane, under certain conditions, we get carbon dioxide and liquid water, and the enthalpy associated with this reaction is negative 890 kilojoules, which means that the difference between the sum of the enthalpies of methane and 2 oxygen molecules and the sum of carbon dioxide and the enthalpy of 2 water molecules is negative 890 kilojoules. But let's say we wanted to know what was the enthalpy of this reaction if water was a gas. Well, if we want to convert liquid water to gaseous water, we would have to put energy into it. Now we know we have to put in 44 kilojoules per mole of water, but in this case we actually have to heat up 2 moles of water into the gas phase. So it's going to double it to 88 kilojoules. Now what's interesting, if we add up these two reactions, we see that liquid water, 2 molecules of liquid water show up on both sides. And the net reaction, if we add up the reactions and the enthalpies, is negative 802 kilojoules. So it didn't matter what pathway we took, if we went by way of liquid water and then up to gaseous water, or if we went straight to gaseous water for this combustion, the enthalpy change, the net enthalpy change, is the same. Now you're probably thinking to yourself, how is this going to be useful to us? Well, what we really want to do is determine the enthalpy of any reaction based on its components, its reactants and its products. So for that we have to introduce the concept of the standard enthalpy of formation. Now you may have seen this before. This is a specific type of enthalpy of reaction. This is the enthalpy change associated with producing exactly 1 mole of a pure substance from its constituent elements at 1 atmosphere pressure and 25 degrees Celsius. These are very specific conditions because these all have to be recorded and analyzed in the lab. So for example, the enthalpy of formation of methane is negative 75 kilojoules, and this is from reacting 1 mole of graphite and 2 moles of hydrogen molecule. So they have to arbitrarily pick what element state they're talking about. We could have chosen 2 different forms of carbon at 25 degrees Celsius, either graphite or diamond. Well, graphite's a little more readily available, so we used that. And it was hydrogen molecule that was chosen rather than atomic hydrogen because it is also, again, much more readily available, much easier to react. So these standards are arbitrary, but they're consistent. Some of these enthalpies of formation are endothermic, such as the enthalpy of formation of nitrogen dioxide. And this is where we introduce those fractional coefficients again. Because remember, enthalpies of formation are for 1 mole. So we had to reduce this reaction, the reaction stoichiometry down to produce only 1 mole of NO2. And therefore we had to have only half a mole of nitrogen molecule. Now, an important piece of information here when it comes to standard enthalpies of formation is that the standard enthalpy of formation of an element, or something in its elemental form, is going to be 0. As you can see here, if we're going from oxygen gas to oxygen gas, we're not really doing anything. Now, this 0 enthalpy of formation is going to become very important later on. So what do we do with these enthalpies of formation? Well, here's our target reaction again, combustion of methane, with gaseous waters being one of the products. What we can do is we can take these standard enthalpies of formation reactions and their associated enthalpies, rearrange them, add them up, so they match our target reaction. And from the sum of the enthalpies of formation, we can get the new enthalpy of reaction. So let's look at the first one. Graphite going to methane. Well, methane is in our target reaction, but it's on the opposite side. It's on the reactant side. So we're going to have to flip our first reaction. So if we reverse it, we keep the quantity of energy, but we change the sign. So this is going from negative 75 kilojoules to positive 75 kilojoules. Now the next one, we have carbon dioxide. Carbon dioxide is on the correct side. It's a product. So we're not going to do anything with this one. We're going to keep its enthalpy of formation the same. And then finally, we have the enthalpy of formation of water. Well, it's on the right side. It's on the product side, but we need 2 of them. So we're going to have to double this reaction, and therefore we're going to double the enthalpy of formation from negative 242 to negative 484. All right, what do we do with this? Well, remember, we're going to be adding up the reaction components, everything on the reactant side and everything on the product side. We notice that we have graphite on both sides of the reaction and 2 hydrogen molecules, so they're going to cancel each other. And we also have 2 oxygen molecules, but they're on the same side, so they're going to add up to 2 O2 on the reactant side. Now, with all of this information, we have our target reaction. We add up the associated enthalpies of reaction, and we get negative 802 kilojoules. Works out great. Now you're probably thinking to yourself, this is very complicated. How are we supposed to do this? Well, it turns out Hess's law gives us a very nice equation for doing this. As long as we know our reaction, we understand the stoichiometry of a reaction, and we have a table of standard enthalpies of formation. So, as with delta of anything, we are talking about the difference between the final state, in this case the products of a reaction, minus the initial state, the reactants of a reaction. So if we can add up the enthalpies of formation of all the products times their stoichiometric coefficients and subtract from that the enthalpies of formation of all the reactants times their stoichiometric coefficients, we can get the enthalpy of this reaction, and we can do this for almost any reaction. So, the sum of the enthalpies of the products, be very careful here. In your charts, you're going to have many different compounds. They're close to each other, and they're not always the same. For instance, we have carbon dioxide here, negative 393.5 kilojoules per mole. It's right next to carbon monoxide. Make sure you don't use that one. And then we have, adding to that, we have water. Now, which water? We've got H2O in gaseous form, we have H2O in liquid form, and it's right next to H2O2 in gas and liquid form. Again, make sure you're using the right one. In this case, we're going to add to this 2 negative 241.8 kilojoules. Add them up and we get negative 877.1 kilojoules for all the products. Now we need to take the reactants. Now, we have 2 reactants, methane and oxygen. Methane, well, we have to make sure we get the right one. That's CH4 in the gaseous phase, negative 75.9. Let's look at oxygen. Oxygen is an element, or it's in its elemental form, O2. It has a standard enthalpy of formation of 0. We can essentially ignore it, but we'll include it here just to show that it doesn't really affect our calculation. So we take our standard enthalpy of formation of methane plus 2 oxygens, which is just 0, and we have negative 75.9 kilojoules. Now we're going to take our products and subtract from that the reactants, and there we go, negative 801.2 kilojoules. This is very close to the enthalpy of reaction of methane with oxygen to make carbon dioxide and water from all the other different methods that we used. So, depending on the table that you use and the method, it's going to vary just slightly, but it's always going to be extremely close.